Right, this thermal radiation first discovered by scientist called James Clerk Maxwell in 1862. So he noted that when current, right, when a changing current, not a constant one, when a changing current, like an alternative current, passes through a conductor, closer to the conductor, electromagnetic waves, electromagnetic waves are induced, right? That we actually learned under magnetic field section as well. Right? When there is a current carrying conductor and electromagnetic waves be induced closer to that conductor. So it was first discovered by this scientist called James Clerk Maxwell. Right. Then, so what is conduction? Conduction process, we already know conduction process that we studied in the heat section. So conduction process mainly occur within solid material like steel, copper, aluminium, right? The heat governing mechanism inside solids are mostly due to this conduction process. Right? Conduction. And second one, convection. So this is the mechanism which covers the heat transfer within fluids. Right? Within fluids, this is the main mechanism which covers the heat transfer within fluids. So if we consider air is a fluid, right? Air is a fluid. And if you observe, when we observe a fire, closer to that fire, so you might have observed small maybe papers or leaves small burnt papers and leaves would go upward, right? Go just straight upward. So that is due to this convection process. Heat transfer is a convection process. But let's say you go closer to the fire, just laterally. So this is as a fire. And when we just go closer to the fire, so convection current happen upward. So these are convection current. But although we don't, so if we go above this fire, then eventually we would feel heat due to this convection current. But when we go laterally closer to the fire, so in that case also we would feel heat, right? In that case also we would feel heat. Another example is if we consider filament bulb. And if you put your hand somewhat closer to the filament bulb also, you would feel some heat, right? So there also you would feel heat. That is due to this radiation, the radiation or thermal radiation process. Third one, radiation, thermal radiation, right? So that is due to that the heat generated, so the heat flowed closer to a filament bulb, or in this case, the fire closer to the fire laterally, right? Laterally. So these are due to the radiation called thermal radiation, and this James Clerk Maxwell scientist, he found that these thermal radiations are just some type of electromagnetic wave. So this is thermal radiation is not a different or the new novel thing. It is just one type of thermal, one type of wave in electromagnetic spectrum. So in electromagnetic spectrum, we know there are a couple of regions dedicated for FM and AM, then ultraviolet, infrared, visible light, and X-rays, gamma rays. Likewise, so this radiation is And so radiation is also a type of electromagnetic wave. Right? This is a type of electromagnetic wave. Radiation is basically due to the heat transfer. Radiation, thermal radiation is the transfer, heat transfer due to electromagnetic waves. Due to electromagnetic wave. So basically the heat transfer happens due to the electromagnetic waves is called the thermal radiation. Right? It's called the thermal radiation. So out of these three methods, conduction, convection process, conduction, convection, and radiation, this radiation process has the highest impact actually. Radiation, the heat transfer through radiation happens the most. What is the reason? Because out of these three mechanisms, the heat transfer through radiation happens the most in the world. Right? In the world, the heat transfer through radiation happens the most because the reason is, so this heat transfer is governed by electromagnetic waves. So for electromagnetic waves, does it need any medium? No. The electromagnetic waves could propagate through a vacuum as well, right? The electromagnetic waves could propagate through a vacuum. So actually, that's what happens. Uh, that's how we receive heat from sun to our earth, right? From sun to our earth. So in between the sun and earth, we can consider that space is a vacuum, right? That space is a vacuum. So the heat transfer, heat received to our sun from the heat received to our earth from the sun is totally due to this radiation process. Therefore, the heat transfer mostly happens due to this radiation. Right. Then let's example heat transfer. So heat received from sun. Heat received from sun to earth. That is that is made due to this radiation process. Right. So let's look at some basic properties of thermal radiation. Right. Some basic properties of thermal radiation. Right. So this radiation is not another thing, it is just a one type of electromagnetic wave. Since thermal radiation thermal radiations happens with aid of electromagnetic waves. Right? This is thermal radiation happen with aid of electromagnetic waves. The properties of electromagnetic waves are applicable for thermal radiation as well. Right? Properties that we learned for electromagnetic waves are applicable for thermal radiation as well. So what are the properties? So one thing is thermal radiation. Thermal radiation happens in a vacuum is equal to the speed of thermal radiation. Or else we can say no medium is needed. Right? No medium is needed. No medium is needed. No medium is needed to happen thermal radiation to occur. Thermal radiation and no medium is needed to occur thermal radiation. That's one property. So the speed of thermal radiation in a vacuum is equal to the speed of light. Right? Speed of thermal radiation in a vacuum uh, is equal to speed of thermal radiation in a vacuum is equal to speed of light. Speed of light, right? So travels very fast, right? Speed of light, 3 into 10 to the power 8. Speed of light. Third one, these thermal radiations obeys the properties that we learned under oscillation and waves. One property is the reflection. This thermal radiation obeys reflection and refraction properties. Thermal radiation obey the laws of refraction and reflection. Right? So thermal radiations, this also obeys the laws of refraction and reflection. Right? So these are some of the basic properties of thermal radiation. Right? Some of the basic properties of thermal radiation. And another thing is this thermal radiation, the intensity of thermal radiation. Intensity of thermal radiation. Right? So let's say there is a source. Sun is here. Right here we have sun. This is sun, and there's a planet here, and the planet there, and two. Let's say the distance from sun to the first planet is R1, and distance from sun to the second planet is R2. Right? So the thermal radiation on the first planet, right? Thermal radiation on the first planet due to the sun is inversely proportional to normally the thermal radiation to a particular point. Let's say if we want to find thermal radiation here and R is the distance, the thermal radiation of a particular point is inversely proportional to the square of the distance. Right? Thermal intensity, actually, intensity of thermal radiation. Intensity of thermal radiation. Intensity of thermal radiation on a particular point. Intensity of thermal radiation on a particular point. Intensity of thermal radiation on a particular point. Intensity of thermal radiation on a particular point is inversely proportional to the square. Inversely proportional to the square of distance from the heat source to the particular point, to the point. Right? Let's say intensity is E, I. It is inversely proportional to the square of the distance R. Right? So these are some basic properties of this thermal radiation. And this is a simple experiment that is done by a scientist named Leslie to observe this thermal radiation, this phenomenon, right? Thermal radiation. So this is called Leslie's cube. Leslie's cube. Right? So this is called Leslie's cube, and this is a thermopile. This thermopile is just a instrument. So this is an instrument that can be used to measure the thermal radiation intensity. Right? Thermal radiation intensity. Thermal radiation intensity. The thermal radiation intensity is just the thermal radiation intensity. Right? Thermal radiation intensity thermal radiation intensity is the uh, amount of energy, right, or the power of power, right, amount of energy, or we can say power, amount of energy that falls on a unit area per unit time. The amount of thermal radiation, the amount of thermal radiation falls on a the amount of thermal radiation falls on a unit area per unit time. Per unit time, so joules, the amount of thermal radiation joules divided by m squared on a unit area per unit time second. Right, so joules divided by second is watt per meter square. So thermal radiation intensity. That is how it is defined. The amount of thermal radiation falls on unit area per unit time. So this thermopile is just a instrument can be used to measure this thermal radiation intensity. And this is called Leslie's cube. So here in the Leslie's cube, so one side of the Leslie's cube, so this side, right? So it is painted to be a lamp black or black surface, right? So it's a black surface. And if we consider this surface, this side, it is polished. It is polished and very shiny surface. The other surface that we cannot see here, it is surface covered with paper, and the other one just the side which is the opposite side to the polished surface is a surface with white paint. And so there are four surfaces. One surface is black, other surface is polished, other surface is just surface covered with paper. The other one is white paint. And other side is painted with white. And this cube is a hollow one. And so this cube is a hollow one. So inside this cube, it is empty. And you can see there's a small tunnel here. That small tunnel here. So boiled water, hot water at a higher temperature can be poured into this cube using this tunnel. Right. So hot water, right? Hot water is poured into this cube from this tunnel. And so when hot water is poured here, so what happens to the temperature of this wall? Temperature of the cube goes up. Right? So when the temperature of the cube goes high, then the thermal radiation happens. Right? Then the thermal radiation happens. And thermal radiation happens. Thermal radiation happens. Right? Thermal radiation happens. Then using this thermopile can be directed towards. So this is just one instance which is given. Right? The thermopile can be directed towards this black surface or this polished surface or the paper or the white surface. By directing this thermopile onto these different surfaces, thermopile onto the different surfaces, this thermal radiation intensity can be found. And the result is the side which is painted in black. Right? Side which is painted in black. Side which is painted with black emits the highest at this side, emits the highest thermal radiation, shows the highest thermal radiation. That's the result here. That is the result obtained from the Leslie's cube experiment. The side which is painted in black emits the highest thermal radiation intensity, and the side which is polished. So the side which is painted in white would emit the least number of thermal radiation, or least thermal radiation would be there on the surface covered in white. And so that is the result obtained from this experiment. It's a result. First one is when the surface is black and rough. And when the surface is black and rough, highest thermal radiation happens through the surface. Through the surface. So the other finding is when the surface is white and polished. When the surface is white and polished. When the surface is white and polished, lowest thermal radiation happens. Right, through the surface. And that is why the test cricket players, when they play test matches, they wear white color shirts, white color outfit. So which this white color outfit or white color surfaces do not, they actually hinder this transfer of heat through the radiation. A transfer of heat through the radiation is hindered through these white colored surfaces. So most of the radiation falls on white color surfaces would be reflected. Would be reflected out. So absorption would be, or the thermal radiation occur through the surface would be less. Right? Would be reflected. Waves would be reflected. Waves are reflected. Motion waves are reflected. And another second one, another experiment called the Crookes experiment. The Crookes experiment. In Crookes experiment, there are, so this is just a bulb, just a bulb, uh, glass, and there are wings, four wings inside the bulb. So if we consider one wing like this, and this wing is field rotate, this wing is field rotate around this vertical axis, and this field rotate around this axis. And the specialty here is, so one side of this wing is painted in black. One side is in black. The opposite side, the other side is painted in white. That's one side of this wing is painted in black, and the other side is painted in white. So from the previous result, right? From the previous result, what can we say? The side which is painted in black would absorb more thermal radiation. At the side which is painted in black would absorb more thermal radiation than the side painted in white. At this side would absorb more thermal radiation than the opposite side. So when more thermal radiation absorbed, what happens? When more thermal radiation is absorbed means temperature of this side, right? Temperature of this side would be higher than the other side, right? So when more thermal radiation absorbed means the temperature of the side goes up. Temperature of surface go up. So there is a difference in temperature on the two sides of the wing. On the two sides of the wing, there is now difference in temperature. Right. Then what happens? Then there are, so this is not a vacuum. This is not a vacuum. There are air particles, right? Filled with air. Yeah. So when now the air particles, right? Air particles falls on this wing. Right? Now the air particles falls on the wing. So when a air particle falls on a wing, what happens? When a air particle falls on the wing, it absorbs heat from the wing. Right? When a air particle falls on the wing, it instantaneously absorbs heat from the wing because it is at a higher temperature. So it absorbs heat from the wing and so bounce back with higher kinetic energy. Right? Bounce back with higher kinetic energy. Bounce back with higher kinetic energy and momentum. Higher kinetic energies or momentum. But when we consider the other side, now what happens? Air particle falls on this black color side of the wing and absorb heat and bounces back with higher kinetic energy. But when a air particle falls on the other side. When the air particle falls on the other side is not that much heated. The other side temperature of the other side is somewhat less than the uh, side which is painted in black. So there are also these particles would bounce back, but with lower kinetic energy or momentum. Right? So on the other side, particles bounce back with less kinetic energy or momentum. On the other side, the particles bounce back with less kinetic energy or momentum. So now we can see there is a difference in momentum of the particles hit on the two different sides of this wing. Right? Two different sides of the wing. So if there's a change, if there's a difference in momentum, what would happen? This wing, would rotate in clockwise manner. Right? So there, here the side having the side painted in black, those particles have higher kinetic energy than the other side. So these particles, air particles would push this wing, this air particles on the black side having higher kinetic energy would push this wing to rotate in clockwise direction. So that is the experiment observed here, right? So there are four wings inside this air inside this bulb, and it is observed that this four wings rotate in clockwise manner. That is due to this thermal radiation happen differently on different surfaces. Okay. So here what you have to identify here, the important thing is this one. When the surface is black and rough, highest thermal radiation happens through the surface. When the surface is white and polished, lowest thermal radiation happens through the surface. So that is the important thing you have to grab. Right. Then the next topic is thermal equilibrium. Actually, that we already discussed somewhat under heat section as well. So thermal equilibrium. So there's also another experiment which is done by the scientist called Prevost in 1791. So he first discovered about this thermal radiation. So thermal equilibrium property. So there is a small container, closed container. Right, so this is a vacuum. This is a vacuum, and so he did the experiment. So this is a vacuum. Right, so this is a vacuum, and a small heated object is suspended on this container. And this is a steel ball. So a small steel ball is suspended on the top of the container, and if the temperature is TA of the steel ball and TB. The temperature is TB on the wall, right? On the wall it is TB, on the steel wall is TA. So TA is the temperature of the steel wall. Temperature of the steel wall. TB is temperature of temperature of the container's wall. Temperature of the container's wall. And since this is vacuum, so since this is a vacuum, and this string is also insulated one. String. Since this container is a vacuum, right? Inside the container is vacuum, and this is insulated string. Only the heat transfer could happen due to thermal radiation, right? So he observed that when TB, the temperature of the container, so the temperature of container can be adjusted from an external source. The temperature of the container wall can be adjusted when TB is kept greater than TA. When TB is kept greater than TA, the temperature of steel ball, the temperature of steel ball goes up until T B become equal T A. That's first case. The second case is when TB, the temperature of the container, is kept lower than TA, the temperature of steel ball. The temperature, just a small observation, the temperature of steel ball, temperature of steel ball goes down until TB equal TA. Right? So in both of the cases, somehow after a certain time, the temperature of the steel ball and temperature of the steel ball and temperature of the wall becomes equal. The important thing here is this vacuum. The container is a vacuum. Inside the container is just a vacuum. So only the heat transfer could happen from the steel ball towards the container through radiation. That is an important finding, a most important finding. The heat transfer could happen through the radiation as well. Right? Heat transfer could happen through radiation because there's no any other method to have heat transfer from the steel ball to the container because it is a vacuum. So no conduction, no convection. This is insulated, no conduction. Since it's a vacuum, no convection. Only possibility is radiation. And since string is insulated, since string is insulated and the container is a vacuum, only possible heat transfer is through radiation. Right? So that's how this scientist called Prevost first found uh, uh, about this radiation property. The theory of heat, which was introduced by Prevost in 1791. See that thermal radiations occur from an object at any temperature. Thermal radiation occurs from an object at any temperature, and the rate of radiation increases with temperature increases. Right? Right. So these are three findings from these from the above experiment that we discussed about this thermal radiation process. Intensity of thermal radiation thermal radiation happens at any temperature. Thermal radiation happens at any temperature. So if there is an object, always thermal radiation through electromagnetic waves happens around the object. So we consider this container as well. From the container itself, thermal radiation, the heat transfer through thermal radiation happens. Right? So if there is an object, the thermal will happen at any temperature. At any temperature. Happens at any temperature. Yes, so thermal radiation happens at any temperature, and it depends on the surface area of the object. Depends on surface area of the object and nature of surface area. Surface area of the object and nature of surface area. So if the surface area of the object, uh, like if it is a big ball, steel ball having higher surface area, this thermal radiation would happen more. And as well as if the steel ball is painted in black, the thermal radiation would happen more than a steel ball painted in white. If the steel ball painted in white, thermal radiation happens slowly. That that are the key findings from those experiments. Right. So I'll give you some time if you need. You can take down any of the anything that is written here. Yeah, so I'll give some time. So when you finish, just let me know. So actually, before moving to the real part here, so this is just a introductory part. So how this is how the thermal radiation phenomena is observed and the key findings of the thermal radiation. So next we count this blackbird radiation. Next we come to the uh, equations. So the most important part. So first one here, this is just an introduction and the equation. We come to this equation, Stefan's law. So before going into that, just take down anything you want under this introduction. And when you finish, let me know.
So can you scroll down?
So after you write down this part, just let me know. I'll scroll down.
So can you scroll down? So can you scroll up? Where is it?
If you are done with this, just let me know.
Done.
All right, then we can move to this black body radiation. Uh, right. So what is a black body? So definitely you might have heard black hole, right? So this is similar to that black body, kind of similar to black hole as well. So what is black hole? So is it a black color hole or something else? Right. So is a black color hole actually a black color hole or anything else? Uh, a black hole, right? So black hole is a let's say some uh, right. So some kind of a but uh, spatial thing, right? Spatial thing which could absorb any kind of wave, right? So uh, it is uh, some object, right? Celestial object, which could absorb any kind of electromagnetic wave that falls on that coming towards the black hole. Right? So black body is also similar to that. So black body is an object, surface, some kind of an object which could absorb any kind of electromagnetic wave, any kind of electromagnetic wave that falls on the falls on it, right? Any kind of mean. So electromagnetic wave, you know, there's electromagnetic spectrum. So this black body could absorb any kind of electromagnetic wave that falls on that, falls on the object. So that is called as a black body, a small hypothetical, maybe not some sort of hypothetical, but in real world means somewhat closer to us. There's no any black body. Right? In domestic usage, no, we don't have any black body, right? Uh, so black body, right? So a black body is so is a hypothetical object which could absorb or emit, both it is correct, which could absorb or emit any which could absorb or emit any type of any type or any kind of uh, electromagnetic electromagnetic wave, any kind of electromagnetic wave, right? Any kind of electromagnetic wave having different wavelengths. Any type of electromagnetic waves having different wavelengths. Uh, right. Right? So when the intensity, that when the intensity of electromagnetic wave intensity of radiation, the intensity of radiation when the intensity of radiation absorbed by when the intensity of radiation absorbed by when the intensity of radiation absorbed by a black body is plotted against when the intensity of radiation absorbed by a black body is plotted against the wavelength against the corresponding wavelength against the corresponding wavelength against the corresponding wavelength. The graph is as follows. Right? So the graph is as follows. Right? So the graph of intensity E. So this is watt per meter square. Right? Watt per meter square. So intensity in the radiation intensity in thermal radiation section is defined as watt per meter square, or the amount of radiation falls on a unit area per unit time against lambda wavelength. Right? So it is found as the shape is as follows. Right? Shape is as follows here, which means, so if you consider this wave having this much of wavelength, let's say lambda 1, this is the corresponding, right? This is the corresponding intensity for lambda 1. So if you consider lambda 2, second wave, so this is the corresponding intensity for lambda 2 waves. And if we consider the whole electromagnetic spectrum, this would be the shape. So you can see there's a peak. Peak lambda, let's say m, and lambda m. There's a peak intensity. EM. So your EM is the peak intensity at the peak radiation, peak radiation intensity. Lambda m is equal to peak radiation in intensity, the wavelength. So this is the peak radiation intensity out of all, and this lambda is the wavelength corresponding to peak wavelength corresponding to peak radiation intensity. This is the peak radiation intensity, and this is the wavelength corresponding to peak radiation intensity. Let's say this is T1. That's for a particular temperature T1. So this is the graph showing the intensity corresponding to each wavelength. Right? For lambda 1 wavelength, this is the intensity. For lambda 2 wavelength, this is the amount of intensity absorbed by the black body. And so there is a maximum the peak radiation intensity corresponding to a specific wavelength, so which resembles that a certain black body absorb the highest amount of radiation corresponding to lambda. Right? So this is T1. Then what would happen? The temperature, when the temperature is increased, what would happen? Right? So when the temperature is increased, right? So when the temperature of a body is increased, eventually, when the temperature of the body increased, eventually the radiation should increase. So if we consider two objects, one is at very high temperature, like 1000 Celsius, and one is at somewhat lower temperature, 10 Celsius, then the amount of radiation emitted by the object at higher temperature should be eventually be higher, right? So all the total graph should be shifted upward when the temperature is increased. Let's say T2 is greater than T1. So when the temperature is increased, all the graph should be shifted upward. But something uh, something different also happened. Some important observation also there. What is that? So all the graph is shifted upward. The important thing is the lambda corresponding to the maximum of the peak radiation intensity. Let's say Em dash, lambda M dash, shift towards left. So that is important factor. When the T2 is when the temperature increase of a body, right? So when the temperature is increase of a body, when temperature is high, the amount of radiation emitted by that black body goes high. That's obvious, right? When the temperature of the black body is high, the amount of radiation emitted from the body goes high. But the important thing is the uh, the the lambda, the wavelength corresponding to the peak value, shift towards left. Shift towards left. So likewise, if the temperature is less, let's say T3 is less than T1, then what would happen? Now the peak would be Eventually, the graph would be shifted down, but the peak value, here is the peak value. Lambda m double dash at lambda m double dash. It goes, it shifts towards right. It shifts towards right. So when the temperature is increased, the lambda m shift towards left. When the temperature decreases, lambda m shift towards right. So that is important observation from here. From the above graph, graphs, it could be from the above graphs, it could be observed that uh, when the temperature of the body is increased, right? When the temperature of the body is increased, when the temperature of the body is increased, the thermal radiation, the radiation corresponding to the intensity of radiation corresponding to each wavelength. The intensity of radiation corresponding to each wavelength increases, and the important thing is the wavelength corresponding to the peak intensity shift towards left. So when the temperature is decreased, so when the temperature is decreased, the intensity of radiation corresponding to each wavelength decreases and wavelength corresponding to peak intensity shifts towards right. Towards right. So you can see there is a relation between this temperature and lambda. The wavelength corresponds to peak radiation intensity. So that is described by Wien displacement law. The relation between temperature of a body and the relation between temperature of a body and wavelength corresponding to maximum intensity of radiation can be expressed from Wien's displacement law. So lambda m T is equal C. So this is the expression. That C is called the Wien's constant. T is the temperature of the body in Kelvin. Temperature of the body in Kelvin. Lambda m is the wavelength corresponding to maximum peak radiation intensity. Wavelength corresponding to peak. Wavelength corresponding to peak. Wavelength corresponding to peak. Wavelength corresponding to peak radiation intensity. C is the Wien's displacement constant. It is 2.989. 2.89 2.89. So this would be one, you don't have to remember this one. 8, 9, 8, 2, 10 to the minus 3 meters Kelvin. Right. So this is the first law that we have. which shows the relation between the temperature of the body and the wavelength corresponding to peak radiation intensity. Then comes to the second law, which is the Stefan's law. At Stefan's law. Stefan's law describes that the total radiation intensity at total radiation intensity means, so this is E1 is the radiation intensity corresponding to lambda 1, E2 is the corresponding to lambda 2. Likewise, total radiation intensity is what we get when we add this E1, E2, E3, E4, E5, E6 and until this curve end. So basically when this curve is integrated, we would get the total radiation intensity. So when the curve is integrated, the area under the curve represents the total radiation intensity. The total radiation intensity absorbed or emitted by a black body is proportional to the fourth power. Right? Fourth power is proportional to the fourth power of is proportional to the fourth power. Right? Fourth power of the thermodynamic temperature of the thermodynamic temperature or temperature Kelvin thermodynamic temperature of the black body. The black body. So ET is proportional to T to the fourth power. So in order to get the remove the proportional sign, a constant is implemented called Stefan constant. That's Stefan constant. It is the total radiation intensity. It is the thermodynamic temperature of the sigma is the Stefan's constant. So sigma is called a Stefan constant, which is 5.67 10 to the power minus 8. 5.67 10 to the power minus 8 watt per meter squared. Kelvin the power 4. And so this value is also not needed to remember, right? We give up. Right. And then consider a black body of radius of surface area, capital A. Capital A. Black body of surface area, capital A. Then the power, the radiation, the power of radiation, that power of radiation, say PT, can be just obtained by multiplying the intensity by the surface area. So ET we have sigma T4 into A sigma T4. The power of radiation emitted or absorbed by a black body is equal, the material just multiply by the surface area of the black body. And so these two laws we have to remember, right? And constant is not needed. The constant would be given, but these two equation we have to remember, right? And most important, this is only valid for a black body. Only for a black body. All right. But the thing here is this black body is a hypothetical one that we assume this is a object which could absorb or emit any type of electromagnetic wave falls on the body. But in reality, in real object that we have, your pen or this book, so they are not black bodies. Right? They do not absorb or emit all the types of light rays, all the types of electromagnetic waves falls on the body itself. So therefore, to modify these equations, these previous equations, we have, the scientists have defined something called a coefficient of emissivity and absorptivity. And so first one is emissivity. Emissivity, simply, noted by simply. So this simply is equal to the total amount of radiation emits. Radiation emit from a real object, from the real object, divided by total amount of radiation emit from a black body at same temperature as the real body. Of the real body. radiation emitted from the real object. So let's say this is E T R real object. So this is E T B black body. Right? So E is equal ETR, and since ETB is always the total amount of radiation emitted from black body is higher than the real object. Always ETB is higher than ETR, right? The total radiation emitted by black body is higher than a real object. So what can you say about E? E is less than 1. And of course, greater than 0. E. And so if we substitute the values here, values means the above Stefan's equation. Stefan's law E is equal E T real object ETB black body is sigma T4 at sigma T4. So the total radiation emitted by a real body is E into sigma T4. At sigma T4. That should come under this section. Modifications of Stefan's law non-black bodies. That for non-black bodies is the equation. Modified equation for Stefan's law. So original equation is just E sigma T4. Now simple is added. So E is called the emissivity. Coefficient of emissivity of a real object. Second one is absorptivity. Absorptivity. Right, so which is described as total amount of radiation absorbed by the object divided by total amount of radiation absorbed by the real body divided by total amount of radiation falls on the real body. So the second one is actually not very much important. What is absorptivity? What's important is the emissivity. Simply total amount of radiation falls on the real body. Falls on the real body. Right. So this modified version also very important in the case of a real object. Right. So this could be applied for real object. So if it is a black body is equal 1. For a black body, simple is equal 1. So these two get equal ETR and ETB, so E is equal 1. Right, so now, so finally, let's consider finally consider an object say black body, consider black body and temperature T naught is kept on an environment having room temperature of TR. And so this is a black body at temperature T naught. So room temperature is TR. So here, as we discussed earlier from Trevor's experiment, if there is a body, whether black body or any kind of body, it emits radiation. So the radiation intensity emitted from the body so here T naught is, assume T naught is greater than the room temperature. The total radiation, it's from total radiation emits from black bodies sigma T naught into the power 4 Stefan's constant. And some other thing also happen. Due to the temperature of the surrounding, right? So heat is absorbed as well from the body. It is E emitted. So total radiation absorbed from the environment is sigma. Now the temperature is the room temperature. So EA. Right? So here the radiation, this radiation intensity. Right? Total radiation intensity emits from the black body is sigma T naught 4. So here we have to apply the temperature of the body. And then in order to find the total radiation intensity, absorbed from the environment, we have to apply the temperature of the room temperature. Then the actual net flow, so you can see here there are red color radiation going out from the black body and blue color radiation absorbed from the environment. Then the total, the net radiation intensity, uh, net radiation intensity emits from the black body. We have to get the difference, sigma ET naught 4 minus sigma TR 4. Sigma is common, T naught 4 minus TR 4. Right? So that in order to find the net radiation intensity emitted from the body, if it is kept at room temperature TR, we have to get the difference of these two. So one is the total radiation intensity emitted from the black body, and the other one is total radiation intensity absorbed from the environment. And the difference would give the net radiation intensity emits from the black body. Right, so that is actually the total content for this first part. For the first part, this matter radiation, thermal radiation, theory, total content related to this thermal radiation part. There are mainly two equations. Means displacement law and the Stefan's law. And the modification of Stefan's law just add E simply for the coefficient of emissivity to the front. And to find the power, we have this. To find the power, just multiply the radiation power. Just multiply the intensity by the surface area. It is the surface area of the body. So relatively a small section is thermal radiation. Next one is photoelectric effect. So before that, I'll give some time to take starting from here, black body radiation. So here this is important. Black body is a hypothetical object which could absorb or emit any type of electromagnetic waves having different wavelengths also the body. So please take down this. So on the black body radiation, you have to write this part and in displacement law, Stefan's law. Yes. So when you finish, just let me know. Here, so when you try to solve the mainly the Stefan's law, right? So in the Stefan's law, we have sigma into t to the power fourth power. So when solving, so I mean, normally when doing calculation, we would be needing the logarithmic table. So you have to use the logarithmic table in this module. Actually, 11th module is somewhat relatively small and easy module, but uh, the logarithmic table would be needed. Yeah.
So could you scroll down? So could you scroll down? So could you scroll down?
So done this part. Then we
So
in
I'd
this
write the
place.
questions.
Sorry.
I'd write the 2 points about the graph.
All right. So basically, in this first thermal radiation part, there are mainly two equations between displacement law and Stefan's law. So by multiplying the Stefan's law by the surface area, the power, the radiation can be obtained.
So could you scroll down? So this is under modification or emissivity absorptivity?
The first one is under the emissivity part until this is greater than 0 and less than or equal to 1. Then under modification of Stefan's law, we have this modified version with the simple E, the emissivity coefficient. Uh, so first you can write this part, the emissivity part until this 0 is greater than 0 and less or equal to 1. Then under modification of Stefan's law, this is the modified version of Stefan's law.
Can't see the screens.
Just give a minute.
So there isn't a modification for absorptivity, right? Or is there?
Yes, so here instead of V, the absorbability, coefficient of absorptivity can be substituted instead of the simply. So depending on situation, we have to substitute the required one. Right, so here for the black body is just a hypothetical one. In reality means much closer to Earth. There's no any actual black body. So when we use this Stefan's law on object, if you want to use this Stefan's law on object, someone at a hot vessel or container, hot kettle, we can use this modified version of Stefan's law. The simple A is the coefficient of emissivity of the object, of the kettle or the object which is considered coefficient of emissivity, and the coefficient of emissivity is always less than or equal to 1. So maximum value for this simple is 1 when the object considered is a black body. Other than that, always it is less than 1. So here when black body or real object is just kept in an environment, this radiation always happen from the object to the outer surrounding. So in order to find the radiation corresponding to that, that total radiation intensity emits from the black body or the real body, we have to apply the temperature of the body, right? Temperature of the object. And the reverse process also happen. The radiation absorbed from the environment as well. When an object is kept on an environment, the radiation is absorbed from the environment as well. So to find that, we have to use the temperature of the room temperature, TR, right? Room temperature. So to get the net radiation intensity emitted from the body, take the difference of these two. So if you are done with this, just let me know. We can go over a couple of questions. So mostly this absorbability, coefficient of absorbability and emissivity, in most of the cases, they are considered same, right? Equal. If it is not explicitly given, we can consider both them as same.
Okay, sir.
Right, then let's try some questions. All right, so try these questions. The first one state that the figures of the variation of intensity of radiation emitted by black body with wavelength lambda as the temperature of the black body increases the maximum intensity. So what happens when the temperature of the black body increases? And that we discussed. So try to give the answer. IM increases, so first answer IM increases, and the position of IM shift towards a longer wavelengths. IM increases and position of IM shift towards shorter wavelengths. IM decreases and position of IM shift towards longer wavelength. IM decreases and position of IM shift towards shorter wavelengths. IM remain constant and the position of IM shift towards shorter wavelength. Right, so the answer is uh, the second one, right? IM increases. So when the temperature of the black body is increased, the maximum intensity IM increases, and the position of IM shift towards shorter wavelength. That is corresponding to means displacement law. When temperature is increased, lambda decreases. Then try the second one. Second one say A, B, C, D are four cups of same size. A and B have rough black body surface, and C and D have smooth shining surfaces. So we know if it is black and rough, both the emission and absorption of radiation happens more. If it is smooth and shiny or white, both emission and absorption of radiation happens slower or less. Emission and absorption happens. A and C are filled with hot water at 50 degrees Celsius. So here you can consider the first one is A, second B, C, D. A, B, C, D. A and C are filled with hot tea at 50 degrees Celsius. B and D are filled with cold tea at 10. A cools faster than C. A cools faster than C and B warms faster than D. No, it is not correct. A cools, so A cools faster than C and B warms. A cools faster than C is correct. A cools faster and B warms faster than C. B warms faster than B. Yes, that's correct. First one. Straight away, the first one is the answer. And then try 11th one. It says a cylindrical copper block of radius r having length 2r radiates energy as black body at temperature T. If this copper block is cut and separated into n identical disks, if this copper block is cut and separated into n identical disks having the same radius r, having same radius r, having same radius r, the rate of emission of radiant energy at the above temperature will increase by a factor of. So P is equal sigma T O A. So P is proportional to A. Right? So P is proportional to A. Here A is 5R squared plus 2 5R into 2R squared plus 4 5R squared. 5R squared 1 plus 4. Right, so when it is cut into n number of disks, it's cut into n number of disks. So let's now consider one disk. So this is 2R, 2R into this length is 2R O n. There are n number of disks. N number of disks. Uh, yes, so area of one disk is 5R square. Actually, here is 5R square in 2. Yeah, because here we have 5R square, other side also we have 5R square. So this should be 2. Here 5R squared into 2 plus 2 5R into 2R of n. R squared 4 5R squared of n 2 pi r squared 1 plus 2 over n. So n number of this. It is 2 pi r squared n plus 2. Right, then the factor, to find the factor, P, P2 is equal A1 over A2. That's all. It's a 2 pi r squared n plus 2, 2 pi r squared, 1 plus 3. It is 3. 1 plus 2 is 3. N plus 2 over 3 is the ratio, the factor. The radiation is increased. N plus 2 over 3. Well, when the body temperature of a person is 35 Celsius, the peak wavelength of the radiation emitted from the body occurs at 9.4 micrometers. When the body temperature of a person is 35 Celsius, the peak wavelength of the radiation emitted from the body occurs at 9.4 micrometers. The body temperature increase to 39 Celsius. The wavelength will be. So we have to get we can use lambda m is equal c. And for the first case, it is 9.4 into t is 35 plus 273 c is 308. The second one, we don't know the lambda into temperature increases to 39. Now it is 39 plus 273 c, so lambda c. So equate these two. What do we get? Seventy-seven or 78 into 9.4. A person with surface body temperature 30 and bottom temperature 20 Celsius, the net rate of loss due to the radiation from the body is proportional to. So P is net rate. P net is A sigma P naught to the power 4 TR to the power 4. So P net is proportional to T naught, which is 273 plus 30 into the power 4, 273. Went to 193 to the power 4. So first one is the answer. Right. So that's there are some other homework questions as well attached to the answer sheet, so you can try them. And that's all about this first section, first subtopic under matter and radiation, which is thermal radiation. So mainly there are two equations with displacement law and the Stefan's law, and this graph of the intensity against the different wavelength that you have to thoroughly understand. And so in next session we will start the photoelectric wave. So thank you.
Thanks.